Hello everyone, my name is Damien Gravela and I work at CS Group as Project Manager. In this presentation, I will talk to you about the 3D Common Operational Feature and simulations of the SafePASS project. Intelligence is only valuable when it reflects the current state of things. By feeding real-time data into a situational awareness platform, the command post can leverage the information aggregated from all sources into coordinated action. This is what the common operational feature is all about. With a COP, such as the Crimson solution, integrated into the response effort, first responders will not be dispersed and they will act on the same insights. The COP system relies on a high availability client-server architecture composed of the following. First, an operational command application to handle crisis situations from within the safety center. This application provides users with a global situational overview of the operational proceedings to manage ship incidents and evacuation. It provides users with the legacy system and sensor information. It also enables them to access the CCTV system and visualize video streams. Second, a safety crew holographic COP application to manage incidents in the field. This augmented reality smart glasses application favors mobility, exchange of information, and communication with the command post. And last, a COP server to ensure data consistency for COP clients and manages access rights. In addition, a gateway on the server allows interaction with other modules like core engine and crowd behavior analysis, which will be presented right after. For the purpose of the COP, CS has generated a digital mockup of the ship that will be used during the project and the pilots. CS has modelized the exterior and interior of deck 4, 5, and 6 with walls and stairs. Plans of the ship have further been simplified and used as ground texture. This model will be improved later on by adding doors and safety features once area of interest for the pilot is defined. The 2D 3D COP, adapted from Crimson to fit the ship constraints and SafePASS requirements, has the following look and feel. A central view allows the user to visualize and navigate on the 3D ship, while dedicated editors allow him to interact with sensors, CCTV streams, incidents, or to replay a session for debriefing. The top bar of the application has been customized with extra components to display weather conditions and to manage the evacuation. On the 3D view, the ship has been integrated into the Chantier de l'Atlantique construction site. A shipbuilding navigator, especially designed and configured, enables users to move virtually to the desired deck, filter the relevant display, and improve orientation. All of the dynamic information is displayed in a compact, yet comprehensive and understandable manner. For example, colored icons and text highlight the sensor type, position, state and values, as well as passenger position. Also, by coloring the ground texture, it is possible to detect congestion by visualizing passenger density per room. Finally, passenger evacuation routes to reach the muster stations are dynamically computed and displayed on the ship. We will now start the integration with the other applications to produce a global operational system. Thanks to the holographic cup, crew members in the field can visualize, manipulate, and zoom on a specific area of the ship to improve their situational awareness. Eventually, they will also be able to view their own location on the ship, as well as locate incidents, passenger positions, and evacuation routes to help them with their assigned evacuation tasks. In case of an emergency, first responders require intuitive and ergonomic interfaces like a hand menu or voice command, which are pending development. Next, we will address the reception of spoken or written messages issued by the operational commander and the upload of information from the field, such as map annotations or pictures. In addition to the COP application, CS has developed a scenario editor. It is a visual programming tool designed to create training exercises and scenarios to validate the system. Most of the basic behaviors have been created. It is currently possible to scenarize the weather conditions, the state of the evacuation, the sensor status and values, as well as the passenger densities. The next step will be to simulate passenger positions and finally to realize complex and realistic scenarios. Thank you for your attention, and we shall meet again at the end of the following presentation for a Q&A session.
Hello, everyone. Thank you for being here today. My name is Marcus Barberis. I'm a Research and Innovation Manager at Exis AI Labs, which is the research and development wing of Exis Software. In today's presentation on novel systems, I'll be talking about the SafePASS core engine. At the heart of the SafePASS core platform, the core engine is responsible for the generation of evacuation routes, the handling of exit signs, the production of warnings and alerts based on information collected from sensing systems, and it also acts as a centralized management and configuration point for the whole platform. Here we can see the core engine and the other components of the core platform, including some that I'll be presenting. All communication between the core engine and other systems are carried out via the communication middleware. In addition, the connectivity adapters carry out the communications with the legacy systems. The core engine is comprised of 3 subsystems: the system management server, known as the CESMS, the location-based dynamic evacuation route, known as the LDER, and the complex event processor, known as the CEP. The end goal of the SafePASS system is to provide a safety management and control platform for the holistic situation awareness and real-time adaptive evacuation strategies. Looking at the different components that I'll be presenting, it is important to note that the latter 3 are not part of the engine, strictly speaking. However, they work hand in hand with the core engine, are necessary for its functions, and are developed by Exis. The CESMS is based on the microservices architecture pattern, as shown in the diagram. This involves developing a single application as a suite of smaller services in order to support different and separate functionalities, while preserving operational efficiency and a loose coupling between the different systems. Functionalities include the monitoring of the SafePASS subsystems, the discovery, registration, and management of SafePASS entities, geolocation-based association of smart devices and actuators within the LDER, and the maintenance of a software registry that the CSMS depends on. The LDER, whose architecture is shown here, contains the algorithms required to forecast passenger movement and determine the optimal evacuation routes. These are based on inputs that allow simulation strategies to be simulated in any scenario, based off a multitude of factors. The two systems that comprise the LDR are the presentation layer, which visualizes the crowd simulation network of the ship, and the communication layer, which is controlled by the simulation server, communicating back to the core engine. Even though the LDR is contained within the core engine, it's not actually developed by Exus. It is developed by CDI, and it allows them to produce evacuation routes and calculate the positions of different people on board. The CEP is closely associated with a common operational picture, also known as the COP, and the crowd modeling server. It is responsible for the real-time detection of hazardous events, data storage, and providing warnings. The first diagram shows the flow of information in the CEP with the respective stages it goes through. Incoming information is processed through the different stages that transform data into appropriate forms, remove irrelevant data, enrich the content, and undergo both granularity and semantic shifts. The second diagram shows the architecture of the CEP. As stated earlier, all communications between the core engine and other systems are carried out via the communication middleware, whose architecture is shown here. It runs on Apache Kafka, which supports low latency delivery while being reliable, scalable, and durable. This is necessary for a system like SafePASS, which handles and processes large volumes of data in real time for impossible life or death situations. Data producers, such as sensors, publish their data onto a gateway. The gateway forwards these messages to a Kafka broker, which publishes the messages to a specific system as required. In addition, a connector is configured to store the messages in a database. Here we have the connectivity layer, with the illustration depicting the architecture. The connectivity adapters are responsible for accessing the transmitted data from the legacy systems. Legacy systems cover important functions like the security systems and the administrative data on a cruise ship. These are functions and sources of data that are important for SafePASS. The aforementioned adapters will receive the message, and after a simple state of transformation, they'll forward them to all the relevant SafePASS systems. Finally, we have the dynamic exit signs. They display the evacuation routes calculated by the LDER. With input and guidelines from partners in the consortium, we have taken into consideration important regulations, such as the size of the screen and how easy it is to be viewed. Down here, we see an exit sign currently found on a Greek vessel. It is static and does not change based on the current situation. Up at the top, we have some mock-ups of the different signs that can be displayed on the dynamic exit signs. Further down, we can see what the dynamic exit signs look like in a real setting as used in different projects. Based on the current situation, the screens will display the necessary signage to guide passengers down the route calculated by the LDER. Thank you for your time and for listening. If you have any questions, they'll be answered at the end of this presentation. Thank you very much.